All right, so I'll be doing an editorial for problems A through C. So yeah, I didn't really do too well in this contest. Um, Honestly, I'll be honest, C was hard to implement for me just because yeah, I had I was flirting with the solution, like with the recursive solution, but uh I never got to submit it because I never got the sample ever. But I just was not. Yeah, whatever. I trolled. So I was only able to get A through B. I didn't do too bad on those problems. Those were not that bad. But yeah. Well, let's just get start the solution. So for problem A, um, yeah, this is a very weird question. I didn't really struggle on it. I solved it at a normal speed. Um, but it's a weird question because basically, let me explain the question. So basically, you have an array of numbers. So I already started. That's okay. So you have an array of numbers, a1, a2, a3, all the way to an, and you want to partition these array numbers into blocks, right? And the idea is that for each block you partition this into. So, for example, they in the sample they use 2 3 5 7. If you partition it into 2 3 and 5 7, the idea is that for each block you partition into it, these blocks represent different sets of integers, and the idea is that in order for this to be a valid partition for each set of integers, it must be such that if you can form a non-degenerate triangle, if you for any three integers you choose from this set, and you can choose the same element again. So for example, in 2 3, that's one set. I can choose 2 multiple times. um I need to make sure that for any of those choosings, right? I can choose a number multiple times, or maybe if I don't want to, for any of those choosings, I need to make sure that all these triangles, all these choosings are non-degenerate triangles, right? So you can see for this, you always have 2 2 2, 2 2 2 3, 2 3 3, 3 3 3, etc. So um, this might sound very very complicated, and so you need to find and the question says, okay, so you need to make sure, does this array have at least two valid partitions? So this might seem like really really complicated, but a trick for A is like they give you like a bunch of this is really weird. Like, I don't know how people think of this type of question. This is a really weird question, but it has a really easy solution. And that's usually what A is, like a or sometimes like or A type of B. Sometimes these problems are just like, but it's straightforward because the first valid partition is, you should think very simply. They even show you it right here. Is you can always A valid partition is always by blocking these numbers by individually. What I mean is that if you have some array, you just partition it element by element. So partition it element by element. That's obviously always a valid partition because the only possible side length in that block is the only element in the block. So for example, if I partition this into two, uh, 3, 5, and 7, for each block, the only possible side length is, like, for example, for block 2, it's only 2. Of course, you can always, equilateral triangle is always going to be possible. It's never going to be non-degenerate because all the side lengths are the same. That's very obvious. So that's always a valid partition. The next partition that you should look for is, can be block individual elements, but then have one partition that has only two elements. And they even show you it here. So, for example, the next optimal, because for example, like the idea is that the reason why that's the next optimal type of partition is because, like, let's say I have multiple elements in my block. Like, if this element works, right? Like, I'm gonna prove that you only need to check that type of partition where you have um like two elements in a block and then everything else is just partitioned by individual elements. The idea is that if I have, like, let's say I have A, B, C, oh my god, C, D, right? Like, if this works and I have some elements like F, G, H, if this partition works, then obviously a partition of A and B, and then C comma D, F, G, H, where these are partitioned by themselves. Okay, let's see, this is H. Then obviously those partitions are gonna be the same. Like obviously this would work. Like it's just very obvious. So you only need to. I don't want to make this too complicated than it actually is, but you only need to make sure that the next type of partition you check is take two adjacent elements, put them in a block, and then have individual elements. So then just basically all you have to do is this question reduces to over all pairs of adjacent elements, um, is there at least one um, such that that partition forms a valid block, where a valid block is like in all possible choosings, you'll always have a valid triangle. So it's really easy to check this because you just like for example for 2 3, like if you 2 3 that's an adjacent element, the only case you want to check is the case where you have two copies of your minimum element and you want to see if that's greater than the maximum element. Because and obviously you don't need to check these cases where they're all the same, but obviously you want to check this case because um two copies of your minimum element, that's like the least optimal for the two smaller side links, or the just you want to, yeah, you would just check this, right? Two copies of your minimum element, um you want to see if those two copies add up to a value that's greater than your largest value. That's obviously the most, like in a triangle inequality case, like you always check the two smallest side links and add them up and see if it's greater than the maximum one. I don't know if they explain it here, but that's basically what you want to do here is in it to see if, like, when you iterate over all pairs of adjacent elements to see if that's a valid block that you could have in your partition. You just want to check if two times the minimum element is greater than the maximum element. And the reason for this is because obviously two times the minimum element um is the smallest possible sum, and we're comparing the smallest possible sum against the greatest side length possible. So that's the worst case scenario. We need to check if that works, and if that works, then we're good. If the worst case scenario works, then we're obviously good. All scenarios obviously work. So I know that might be like a little complicated, but it really isn't. So if you check the code, all I'm doing here is I'm iterating. I'm gonna have my elements, right? And basically I'm iterating over all pairs of adjacent elements, and I only care about the maximum and minimum element. I want to check if twice the minimum element is greater than my max. If twice the minimum element is greater than my max, then that pair of adjacent element is a valid block. And obviously this works because the two partitions I can have are individual elements, and then that valid block surrounded by individual elements, and then that will be my solution. So yeah, probably pretty straightforward there. The really the insight is always just like think very simply, like never think complicated, like you know um okay, this question, um I think there's like a different solution than mine, but I'm gonna so there the solution the my I used did people use prefix sums or something? Yeah, so I didn't do prefix sums. I actually did a better, not a better solution. Sorry, I did another solution. I'm not sure if it's better. They did prefix sums. To be honest, I'm just gonna give my solution because it probably covers the same thing. So in this question, it's like, let me explain what's going on here. So yeah, wait, what's this question again? Oh, okay. So yeah, you basically have a set of intervals, and the idea is that like you want to solve for each interval, you want to solve it independently. So you basically for each interval you want to choose a value from that interval, and it must be such that once you choose a value from that interval, that value has to be unique, and then you have to be able to choose the other for the other intervals. So independently for each I, for that I, right, for that interval you have, you must choose a value, you must assign a value to that interval. and the value that you assign to that interval has to be like some number within that interval. Once you have that value, it has to be such that when you assign values for the other intervals, that value you have is unique, right? When you assign it for the other intervals, the value that you have is unique. It's not duplicated. So I think um, my problem is straightforwardly explained. Um, so the insight immediately, just by looking at the test cases, is that um, um, if you have, for example, let's say you have some value interval from A to A, right? If another interval appears to be A to A, then you're cooked. You only have one option to choose. You only have one option to choose, right? So if you only have one option to choose, you're cooked, right? And similarly, the idea is that if I have some interval in general from like A to B, um, if I have intervals that have to be A and then have to be, let's just use a not let me not use A to B. Let's say my interval is from 1 to 3. Maybe I have 1, 1, 2, 2, 3, 3. Basically, for some intervals, there are going to be only one possible value that I can be for some intervals, right? This interval has to be 1. This interval has to be 2. This interval has to be 3. And if those intervals have to be 1, and those intervals have to be 2, those intervals have to be 3, then for this interval 1, 3, I know that there is no value that I can assign to it such that it is unique, which means that I would assign that answer would just be 0. So the idea here is my first thought actually was you know though there are values that there are intervals such that like um there are intervals such that like there's only one possible choice, but for an interval what I how I thought of it late when is that for some interval L to R, you want to see, like, let's say you have, so these are values that like um you cannot, so these are there's a set of numbers of there's so basically for all like pair intervals such that L and R are the same, those are the set of numbers that you basically can't, like, for when you're on some interval LR, you basically cannot assign those values. You can't assign for that interval LR, you can't assign the value for a number that is within that set. And that set that I'm talking about is all the intervals that are that in which L and R are the same. So like this set is, for example, in this case it would be like 1, 2, 3. I can't, for my interval 1 to 3, I can't assign those values. So basically there's two sets. There's a set in which you can't assign, there's a set in which intervals can't be those values, and there's sets in which there can be those values. So for example, let's say for example it's 2 to n, so the set, this is like you cannot be those values. But for can, if let's say n is like 3, because the values, the ranges can be up to like 2n right here. I can be 4, I can be 5, I can be 6. I can be 4, I can be 5, I can be 6. So the idea is that for some interval L to R, okay, for some interval from L to R, the idea is as put. I want to check, I'm trying to see which value from L to R can I assign this to. Well, it must be in the set of values that I can assign it to, like in this can set, right? In 4, 5, 6. So the idea is that I want to see in this set of numbers that I have, I basically have reduced this question to, I have an interval and I have a set of numbers. Is at least, can I find one number that is contained in this interval? That's what this question is reduced down to. Look, if I have a set of numbers and I have an interval, in the cannot find me one number that is contained, one number in that set that is contained in the interval. That's all the question is. And again, the reason this question is because For my interval LR, I'm trying to see what value can I assign this to. What value can I assign this to? What values are forbidden? The values that are forbidden are the intervals that in which L and R they're the same. Those are the values that are forbidden. These types of values in which there's an interval such that a value A is forbidden if there's an interval in the input where it's like AA, right? Those values are forbidden. So I can assign it to those, but I can assign it to like 4, 5, 6. So I want to see like is at least one of those values in LR. And the idea is that to solve this problem, it's very simple. I only care about like it's just simple set dot ceiling, right? Think about it like this, right? If I have a set of numbers, I would just find the number that obviously to be in this interval, you have to be greater than L, right? You have to be greater than or equal to L, correct? To be in that interval. So if I have to be greater than or equal to L, I also have to be I'm gonna set dot ceiling of L. And the idea is that I have to be greater than or equal to L. And once I guarantee that I'm greater than or equal to L, once I guarantee that I'm greater than or equal to L, I only care about the number that is the smallest, right? So if I have all these points that are greater than or equal to L, all these points over here, I would only check the smallest one of them. Because now that I'm greater than or equal to L, the condition has to have to be less than or equal to R. So I would only check the smallest of them. And so then in that set of numbers that I can be, I would do set dot ceiling of my L. And then I would say, okay, by ceiling, I've guaranteed that it's greater than L. But now I have to check if that is less than or equal to R. So it's a simple greedy. And if it is, we're good. So this is how you code it. There's actually a nuance edge case that you have to do. But what I do is I want to check if this is a forbidden value. A forbidden value is if in the input I have for a forbidden value a value A is forbidden if there's an interval in the input such as it's AA. So I go through, I mark all my bad values, and the reason why I'm doing this guy is because um, let's say you have some value 1, 1, right? Like there's this test case that actually is pretty nice. There's this edge case over here, like you can assign 1 to this value. Like 1 is not forbidden. Like for example, the idea is that like the edge case is like you might forbid a number. Like for example, if you're trying to find what values to assign 1, 1, you can assign it to 1, right? But for that case, 1 is not forbidden because it's obviously there. Maybe if 1, 1 appears more than once, like over here, then it's going to be forbidden. But for that case, it's not forbidden. So for example, for that case, it's not forbidden, and I just want to you have to just deal with that edge case. It'll be very obvious once you code it and then not get it, but that it's just a simple edge case. And luckily they actually gave it to us they're nice enough to give it to us in sample. But yeah, basically in my set, I'm going to add values that I can be. So that's my set. So basically not bad values. And I'm going to go in. And this is just the case where like, for example, if L and R are the same, but this interval only occurs like one time, this interval like 1, 1 only occurs one time, then it is not a forbidden value. We're gonna actually make sure that we can add it for that case. When I'm done with it, then I'll just remove it. But for that case, it's not a forbidden value. After that, then it's obviously a forbidden value. But then we just do what we do is we get the best value that we need to check. One that's just greater than or equal to L, and we only care about the smallest one. That's exactly what set.ceiling does. And I'm going to take that value, check if it's less than or equal to R, and if it is, then from the can set, there is one value that I can grab that's within that interval, and my answer is going to be 1 for that, and I print it out. Boom. So that's pretty much it. Now there is a solution. I'm pretty sure, like if you do the can't set, there's a solution with prefix sums. Me personally, I thought can was easier. I don't know. I think I was tripping with can. I tripping with can? I don't know. I don't really care. I rather do another question than think about this other version. But I think it's a pretty clean way to do this question. So Yeah, this question is problem C. Yeah, so this question actually gave me a pain. Pain to do. But uh here is this question as follows. Is you have this segment 1 to n, right? And the segment 1 to n uh okay, well, yeah, and she has a lucky value. It we don't care if it's lucky. Basically, it's just this. Our answer is currently 0, and the idea is that um, the question is pretty straightforward. You have this range 1 to n, and then you calculate like the midpoint of that range. And the idea is that like you split the range accordingly to the midpoint. So if it's even, for example, if it's like 1 to 8, you would split into 1 to 4 and then 5 to 8. Um, but if it's like an odd number, like 1 to 9, you would split it like from 1 to 4 and then from 6 to 9, like just from the midpoint. Like basically, you want to ensure, in this way, you ensure that like the length of each range is the same. That's basically what's going on. And the idea is that like when we're on a range, if there's an odd amount of numbers, then we add to our answer, we add the midpoint of that range. Why? I don't know. That's what the problem says. And the idea, and also question also says this question seems extremely contrived. Like it's just like, well, contrived in the sense that like there's not really a natural storyline. You just have to say exactly what you want to happen. But the idea is that like if the number of numbers in that range is less than k, strictly less than k, we don't care about it. It does not contribute to our answer. We stop observing stuff. We stop splitting it. We stop splitting it into anything. We basically don't care. We don't split it. We're done. Okay. So in this question, the way you want to observe this question is by drawing it out. Definitely. So draw it out on the smallest test case, right? And then you'll start seeing the logic. So for example, if you have 1 to 7, right? My midpoint is the median of the numbers 1 to 7. That's basically what this thing is, right? The median. So it's 4. Okay. So it's going to be 4. And then after that, I'm going to split this number into 1 to 3, just, and then the number 5 to 7. And then after that, my midpoint here is 2. My midpoint here is 6. I split this into 1 to 1, 1 or 3 to 3. Okay, so that's how my tree looks like. And the idea here is that for every range will contribute something to my answer. For example, since the midpoint of this range, since you if you have basically if you have an odd amount of numbers, right? Then then for that range you just add the midpoint. And you stop observing here because in this case, k is equal to 2. We don't care about ranges that have strictly less than 2 numbers in them. So all these ranges are just stop splitting, right? Um, and k is like 10 to the n. Yeah, we just stop caring about those numbers. Okay, so but and then our answer is in this case is 2 plus 4 plus 6 because for each range that has an odd amount of numbers in them, you add that to your answer. So it'd be 12. So the straight observation here is your mindset should be log n because n is like 10 to the 9. There's no way you can't have any n times or n, but no, it should be log n, right? So you should be thinking of like how can I solve this question in log n? That should at least be your mindset of like logic, right? So the idea here is, and this is actually what I observed, but I wasn't able to like code it fully, and like it was like kind of like a very abstract idea for me. but I wasn't able to concretely do it. But this is what I observed is when I have my range, I only care about oops. So when I have this tree, I only care about the sum of the lucky numbers in the or what I'm saying is that like okay, so if I split this into the tree, what I'm caring about is I want to find like the sum of the lucky numbers, right? I only care about the lucky numbers. Notice that the tree is basically symmetric. Like basically this is an observation you have to make about this tree in order to speed this stuff up. Is the tree symmetric? And what I mean by this is that these ranges are these ranges, except those ranges are just shifted by 4. Like 1 3 is the range 5 7, but it's shifted by 4. 1 1 is the range 5 5, but it's shifted by 4. 3 3 is the range 7 7, but it's shifted by 4. The idea is that when you split this tree into a left and a right subtree, the ranges in that tree and the ranges in that tree, they're symmetrically the same. They work effectively the same. The only idea is that the center is M. They just deviate around the center. And so they're symmetrically the same, which means that all the lucky numbers that I added in my left subtree is basically going to be all the lucky numbers that I add in my right subtree, except the right subtree for all those lucky numbers, they just differ by the midpoint, by the center, right? They just differ by the center. That's all it is. The reason why this is very important is because I'm basically saying that if I just think of this as a tree, right, and I think of these each tree has a value, right? So I care about the. I want to find basically the sum of lucky numbers is the answer. That's the answer I'm trying to find, right? So for each node, I care about the sum of lucky numbers, right? This means that like if I care about the sum of lucky numbers, dude, I don't care. I don't like when I build this tree. I don't have to go left and right. I only have to go left. Because when I'm going left and right, this is causing me to it's too much. Because going left and right, you'll build the entire tree, and that's obviously not what they want you to do. If you want to think about like the time complexity, well, just think about it as in the last level you might have 2 to the log n, because there's gonna be like log n levels, and if there's log n levels, you have like n. So it'd already be n plus some. It'll be like it'll already be too slow, right? But for each node, but that's because I'm going left and right. I only have to go left because I know my right subtree is symmetric. It's the same as my left subtree. So I only have to go left. So for each node I care about the sum of lucky numbers, but I notice that I only have to go left. And if I'm only going left to left, 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 I'm basically just going through the amount of levels. What's the amount of levels in this tree? It's log n. If you have n nodes, the amount of levels is log n. This should be very obvious. I only have to go left. Left because of the symmetry. So, because the idea is that the right subtree is basically the left subtree. So I'll just use right is basically the left, except it's the midpoint, which is your shift, midpoint plus the number of lucky numbers, because you basically know that it's a sum of all the lucky numbers in your left subtree, but now they're all shifted by the midpoint, whatever your shift is. So like the midpoint, and that and on a level on a level, for example, on the first level, the midpoint would be n plus 1/2. It's gonna be 4. On the second level, you notice that um, on this level, the midpoint um, it cuts in half. So, for example, it'll just be like you'll see when I get into the code. But the idea is that it's gonna be the midpoint times the number of lucky numbers Bro, turn this off, bro. God dang it. So it's midpoint times the number of lucky numbers, and that's it. Basically, you need to find what the shift is, but that's all it is. They're symmetrical questions. So the idea is that when I'm saying okay, so then and so I need to know. So that means I for each node I care about the sum of the lucky numbers and the number of lucky numbers in that subtree. So basically, the idea is that okay, for some node, I only care about going left. I don't care about going right. I can go left, and so if I can go left, because they're symmetric, then all I have to do is keep track of the sum of the lucky numbers and the number of lucky numbers. So then this boils down to a code question, an implementation question. And the thing is, I made this observation. I didn't really keep track. Okay, whatever. But the idea is that this just boils down to a code question. So I think I actually have it here. I might as well just go here. So the idea is that on your tree, you have some range, right? The range you're only going left. So basically the ranges are just from always going to be 1 to some number, like 1 to 7, like 1 to 3, 1 to 1. You always go left because you never need to go right because you know that um you can the right subtree. So for example, the right subtree is just going to be the sum of that is going to be that, and then you can just add it together to get that node, right? So that's what you can do. So for example, what I'm going to do is I'm first going to say when I stop observing it, when the number of numbers is strictly less than k, the sum of lucky number, I'm not going to do anything with it. So that means that I won't. I'll have zero lucky numbers. The sum of lucky numbers will be zero, and the amount of lucky numbers, right? Because this is basically so the array. So nk will return an array, and that array will be sum of lucky numbers for my first element. So basically, what's going to go is that so then my idea is that so if n is less than k, I'm obviously going to have zero. The sum is going to be zero, and I'm going to have zero lucky numbers. Now it's just some casework, right? What I want to do is when I'm on my tree, I only care about my left guy. Just give me my left guy. Give me the sum of the lucky numbers in my left subtree and the amount of lucky numbers we have. And then I can get my right subtree because I know it's the same thing. So that's what I'm gonna say. Just give me that array, right? Return to me that thing. And then what I'm gonna do is I'm gonna do casework, right? If n is even, right? If my range is even, then I know that my sum of lucky numbers is basically it's gonna be the right subtree will be it's gonna be twice the left subtree, so my left, because I know my right subtree is my left, but plus some shift, and then I'm gonna add the shift. Now I'm gonna add the number of lucky numbers I have in my left, which is just that, and I have to figure out what this shift guy is. So this shift guy is, it's just like math nuances, right? So basically, that midpoint that you'll have is given that you're on some level of this tree. Like first they deviate around m, right? And then after it'll be smaller. It'll like the center if you're cutting a range from 1 to n, then boom boom boom, the center at first the center is m, right? So at first it's Oops. Oops. So, and we'll let n be like the range. So, for example, um, if the range is 1 to 7, we realize that it's gonna be like the shift would be 4, and if the range is 1 to 3, the shift here would be 2. So it's always just like the middle of my range. So for 1 to 7, it would be like m+1/2. So um, and you could do if you want to, you could do this, but it's basically just whatever your midpoint is in the range, right? If it's even, I mean, it doesn't really, you don't have to do like n+1/2, but you can just if you want to. But basically, that's your shift. That's the shift. That's a value that's a center, right, of that range from 1 to n, because you know that it's being split by that range. So those ranges, that right subtree is by that. So if you have this range and it's being split into the left and right, obviously these ranges are shifted by the midpoint. And to grab the midpoint of that range, and nk, I'm doing f of nk where n is like the number of 1 to n. Then the idea is that that would be my range, and I can just basically say that for this case, you're gonna have that times the number of lucky numbers, and that's how you shift it. And then the number of lucky numbers is basically, it's always symmetric, because this node itself is not a lucky number because it's even. It doesn't if a range has an even amount of numbers, it's not going to give you a lucky number. Or by lucky number, I mean like, yeah, you know what I'm saying. Lucky number as in like it'll increase. It's not going to increase if it's even. So I just do left times 2. In this case I would do +1, but in this case it's the same idea here. Um and the only reason I'm adding 1 over this is because the node itself, that gives you since it has an odd amount, the value increases by the midpoint. So I also have to add the midpoint as well. And then I also have to add the fact that for the right subtree, they're all shifted um, by uh, by this, and you need to find the amount of numbers in the left subtree. So it'd just be this. So it just boils down to like a recursive question. Um, it's a little annoying, but basically this is like what you have to do. And the idea is that for each node, you care about the sum of lucky numbers, the number of lucky numbers, but you only have to go left. Um, and you have to keep track of the range, and because we're only going left, the range, the node can just be from like 1 to n. You just have to keep the node can just be labeled as the end point, which is n. And so that's what it is. So yeah, that's basically the solution. Yeah, there we go.